Okay, so my talk this morning is really just talking about open source processor intellectual property. And it's a bit of a mouthful, but I'm going to give an introduction to the RISC-V ISA, talk about the challenges associated with SoC design in general, and specifically open source IP. Mike's going to get into that in much more detail. Then I'll talk about a nonprofit ecosystem that is being built under the Open Hardware Group banner and a family of open source cores called Core 5. Talk about how that group is structured at the end. But before I start, show of hands, before you saw the information about this event, how many of you had heard of RISC-V before? Nice. Yeah, that's good. How many of you have downloaded the spec? Oh, very fewer hands. How many of you have read that spec? Oh, sort of, because it's light reading. How many of you have an active project using a RISC-V core that you either developed or somebody else developed or what have you? More people than downloaded the spec. That's good. All right, so I actually have a fair amount of history with RISC-V. I'll talk about that in a little bit, but to give you an appreciation for where this came from and what it is, the computer science department at UC Berkeley, and for those of you that have a Patterson and Hennessy textbook or used one in your engineering undergrad, that Patterson, Dave Patterson, is still very active with UC Berkeley. He's actually retired now, works as an advisor for Google, but he's still very active at UC Berkeley and was quite active in this work back in 2010. The team there that started the whole RISC initiative back in the early 80s started to look at what they could use as a pedagogical tool for their next generation of programs at UC Berkeley. So they started this 3-month project because, hey, we've done it before. We've, DLX, we've invented a bunch of ISAs before. We'll just bang another one out in the spring. They said, we'll have it ready for the fall. And that turned into the May of 2014. That 3-month project was almost a 4-year project where they released the frozen base spec for the ISA. Many, many tape outs along the way, lots of research papers, and that was really cool. And a lot of industry traction, right, which kind of surprised them a little bit, and I'll talk about that a little later. This part's important, right? It's not RISC-V, it's RISC-V, Roman numeral 5. So you are all now deputies of the brand. When you hear someone say RISC-V, you say, no, you tap on the shoulder, say, hey, no, mate, it's RISC-V, that's a 5, right? And there literally are 4 previous versions of this research work that was at UC Berkeley. So RISC-1 and 2 are kind of obvious, so they kind of lost the naming recipe on SOAR and SPUR, but nonetheless, there were 4 previous projects to this RISC-V initiative at UC Berkeley. And like I said, if you have a Patterson and Hennessy textbook from when you were in undergrad, it's that Dave Patterson, pretty cool guy. So, okay, they start working on an open, free and open ISA, and like, well, why isn't there one really that's been successful yet? Every other interface in a computer system that you can think about, there's an open standard associated with that interface, freely shared and used by all developers across the industry. There's definitely been attempts, right? There was a project called OpenRISC for a while. There's certainly the Spark stuff has been opened. We've just heard from the IBM folks that they're going to open power, but they're the only ones who can actually change the ISA. So it's been interesting to see that there really has not been an open specification at the ISA level. Instruction set architecture, by the way, that's what an ISA is, if that's new to some of the folks. I'm making a couple of generalizations in here that I probably shouldn't. And RISC is reduced instruction set computing, right, as opposed to a CISC architecture, complex instruction set computing. x86 is an example of a CISC machine, although they've done lots of things to it to make it feel and look like the attributes of RISC architecture, but it's a much, much bigger ISA. So we'll talk about some of those differences later. So why isn't there one? Let's take a real-world example of what an SoC, a typical SoC, and I've got a Tegra SoC up here from NVIDIA. What does it typically look like? There are dozens and dozens of processors on a modern SoC today. They're not all exposed with an API for the user to program. A lot of them are an internal black box where there's firmware that gets loaded onto it. You never even see them. And what's really terrible about it, you can understand how it got this way, is most of these processors have a different ISA. They have a different tool chain, a different programming stack. They're all different. And so when you think about this from just the elegance of an engineering perspective, if we went into, we're working together and we go into our boss and say, guess what, we're going to come up with a new SoC design. And by the way, we're going to use half a dozen different types of processors, all of which have different instructions and are programmed differently. And we'll have to maintain the tool chains on like 3 or 4 of them. But some of these we'll be able to get either commercially or through the open source environment. We should get shot. There's no technical reason for this. So why? Why are there so many? And do they have to be proprietary? Well, the answer is no. And boy, geez, wouldn't it be great if there was an ISA out there that we could take advantage of, that everyone could use across all computing devices from a performance standpoint, from the very low end embedded stuff right through to server class machines. Wouldn't that be cool? Well, guess what? So how is RISC-V different? Well, first of all, there's the hindsight. It's really easy to do better things once you've done something for 20 years, right? So the Berkeley team, the hindsight of experience, led them to a lot of very interesting decisions that they made around architecting the RISC-V ISA. It's far smaller than any commercial ISA. In fact, the base integer spec is less than 50 instructions. And it's a clean slate design. Lots of work went into researching where every instruction has come from pretty much in all other architectures, whether that's DEC alpha stuff, old PDP-8s and PDP-11s, right through to x86 and ARM and everything in between. Bit slice machines, 29K stuff from AMD. Yeah, I've earned my gray hair. All right, lots of old stuff. But they did a lot of work understanding where all those instructions came from and why they were used and implemented, and then came up with a clean slate design. And this part's particularly important. There are no microarchitectural dependencies or techniques built into the ISA that presupposes a specific implementation. So the ISA spec itself stands on its own. You can implement those instructions and your microarchitecture however you want. And the next 2 points around the modularity and extensibility are probably the biggest differences between RISC-V and any other instruction set architecture. And that is the fact that it's a modular ISA, so it's not one contiguous list of instructions, and in order for you to be compliant with the ISA, you have to implement every single instruction or your stuff will fall over. The standard is broken up into, or the specification, I should say, is broken up into standard extensions. Which makes it really easy to tailor your design to the right performance metrics that you're trying to hit for the data payload that you're trying to target this device for. And that modularity is leveraged by allowing for user-defined instructions as well. So there's a space in a reserved section in the opcode space where you can roll your own instructions, whatever secret sauce algorithm that you want to have in hardware, implement that machine, kick it off with a custom-built accelerator as an example through the user-defined space. And we also take advantage of the fact that with the extensions, we don't have to rev anything. So it's a very stable design. So as an extension is released through the industry body, the RISC-V Foundation, that extension will never be changed, even if there's something wrong with it. It'll get corrected in a future extension that gets added. So there might be some functional overlap, but that extension that you would put into a device and then have deployed will always be supported, warts and all, in the marketplace. So that stability is very, very important. So new optional extensions as opposed to revisions of any released extensions. So I'm going to walk you through sort of the extensions in a little bit. And what's important here is the simplicity of the architecture, as well as you dial up the extensions that you want to have in your device based on the performance and application that you're targeting as you're designing a new device. So there's a bunch of standard extensions for integer multiply divides, atomic operations, so like load store, read, modify, write kind of atomics, a series of double and single precision and quad precision. And then this G notation is seen as a general purpose collection of all of those extensions with an IMAFD set of extensions in your processor. So for those of you that are old, like me, and maybe you played with bootstrapping switches on the front of a PDP-8 or PDP-11, or had an old IBM machine where you had a green card. A green card was a thing that geeky guys carried around in their back pocket and had all the assembly instructions of machines in those days. And to show the simplicity of the ISA, I'll build out the RISC-V green card. So this is the base instruction set of RV32I. So that means 32-bit integer instructions. That's the nomenclature. And that's the less than 50 instructions that would be in your machine if that's the only extension you implemented. And then we'd add 14 more for privilege mode, 8 more for multiply divides, 11 for atomics, and then the floating point, the different precisions of floating points, compressed mode, and then repeat it again for 64-bit and 128-bit variants. And there's your green card. Now, it's kind of hard to read. I need to put glasses on when I'm reading it, but it is very legible. And if you're younger, you can read it without glasses probably. So that's pretty cool. So I kept referencing the Patterson and Hennessy Computer Architecture and Design, Organization and Design textbook. By our count today, there are more than 300 universities now that have switched to this updated version of the textbook that implements the RISC-V ISA as a teaching tool. And in fact, I think I saw some folks who already have one. I think you have one, you could hold it up and show folks. Probably, like I said, more than 300 universities around the world that have integrated RISC-V either at the undergraduate or graduate level or both as a teaching tool for computer architecture, which is pretty cool. The Mona Lisa book in the middle, and I think there's a few folks in here that already have that as well, is a pretty easy, simplified reader, RISC-V reader, to give you the origins and syntax and format of every instruction. So it's quite good. So what's this foundation? What's it look like? So I actually started hanging around with the Berkeley guys in the fall of 2014, learning more about their work on RISC-V. And they came, when I said earlier that they had lots of tape outs and lots of publications along the way as they were doing their research work, they came to the conclusion that there was plenty of folks that were following their papers. I mean, those of you that are in research-based roles, you publish a paper, and that's great. You get points for that. Maybe somebody reads your paper, that's even better. And maybe then you get feedback even from the reader community, and that's fantastic. So what was happening with all the research that they were publishing is, as they would change things from one research initiative to another, they were getting feedback from industry around, hey, wait a minute, don't change that. What you did back there, this was really good for these reasons. And so they had a lot of community involvement in the work that was going on around the RISC-V research, which led them to the conclusion that this can't just be a project that exists inside the four walls at Berkeley. It needs to graduate, grow up, and basically be shepherded by an external organization. So we had the mandate to create a governing body. The RISC-V Foundation is what it's called. We filed, I started it with the team from Berkeley, and we filed articles of incorporation together with 40 other sponsoring companies to create the RISC-V Foundation in August of 2015. And I ran the foundation for the last almost four full years. up until this May. And I left, and one of the reasons I left is what we'll talk about in a few minutes. And just so you know, so that what the foundation does is it helps to educate around the ISA and releases the specifications only, no implementations. The RISC-V Foundation loves all implementations, and we'll talk about that in a minute. It's a good opportunity to, any one of us, we could start a processor company in your kitchen tomorrow. Don't need lawyers, don't need anybody, assuming we know what we're doing. We download the spec, and we just start going. And the Open Hardware Group, which we'll talk about shortly, is a member of the RISC-V Foundation. So you can go to risc5.org. I just got a member at a glance screenshot here. You can go there and check out all the members. Any company who is involved either at the chip level, software level, tools level, or system level has an active project somewhere in their company around RISC-V. It is staggering the adoption that this is seeing. And one of the reasons that we wanted to organize this event and continue to have an anchor event here in Ottawa is to make sure that our Canadian ecosystem is keeping up with the rest of the world. I have seen firsthand what's going on everywhere else. We got some work to do. Okay. What are some of the challenges associated with chip design? Oh, geez, the tools are expensive. Takes, mask sets, if you're doing anything in deep set micron, it's impossible. But if you combine the software work, the actual RTL to code the chip and design, and the verification work and physical design, the effort associated with that compared to the overall cost of the SoC is around 90% of the effort. So, for highly differentiated IP blocks, that's a good thing, absolutely. If everybody has the same control processor on their SoC, not a lot of differentiation there. Maybe we can all share that and help everybody get to market faster, and more importantly, focus on the part of the device that you want to really have differentiation around. Sounds good, but are you the person that's going to walk into your boss's office, put your badge on his desk, his or her desk, and say, oh, guess what? I found this cool core online. Let's put it in our next chip. And we'll get to market faster, everything's wonderful. Oh yeah, it's a GitHub repo that some university grad posted, and university grads are great, don't get me wrong, but it might not be verified to the same degree that you would typically have when we're talking about commercial IP to integrate in an SoC. The other part of it is, where's the roadmap? Okay, great, we're going to use this core. So when you do the next version of that SoC, is there going to be a next generation version of that core that you can use? And as your roadmap for your product goes forward, there's a family of IP and to support that functionality. What about the tool chain and the porting the OS and all the drivers and all that stuff? Where's that going to come from? And then, of course, there's the licensing. It absolutely has to be permissively licensed. No major SoC vendor will accept legally the need to have to give back. They want to give back, and they will, but not everything, right? There needs to be an opportunity for leveraging the open source ecosystem, contributing to it, but then still having room for secret sauce things that happen sort of over on the side, right? So permissive licensing is a must-have. For 20, 25 years now, the software ecosystem has understood how to evolve an open source software environment. And on the hardware side, we've kind of been looking over there at our software friends going, geez, I wish we could do that. None of these things have really been dealt with adequately in the industry. So this is what we're trying to do with the Open Hardware Group, solve this problem. So great. One of the first things, if you're going to have an open source processor, you really need to be able to distribute the ISA freely. And you certainly can't do that with any of the commercial ISAs. So fantastic. We have a free and open ISA. That's perfect. Yay, good. RISC-V exists. Like I said, any two of us could start a processor company in your kitchen tomorrow, and hallelujah, innovation, new frontier, great. So now let's sort of step back from that for a second. If we think of, let's just say this room represents all of the ecosystem enablement for a new processor on the planet. So this is it, this is what we have. And we drop a core in and say, hey, let's spin up the OS ports and device drivers, tool chain, application software for this new core. We get everybody working on it, that's great. And then we say, hey, guess what, here's another core, we'll drop that one in. We want to spin that one up too. Okay, so now we're going to divide the resource in half, and then we're going to drop in another one, and drop in another one. So unleashing a new innovation frontier with the opportunity for multiple cores and implementations is great, but at some point, we don't have critical mass to actually enable those new innovations and make sure that they're sustainable over time. So it's a little bit of a conundrum in terms of open innovation is fantastic. How as an ecosystem do we actually take advantage of that and have critical mass behind a handful of implementations? And if you look at the early days of Linux, there were hundreds of distributions. And there are still more than most people realize, but now there's really only a handful of distributions, and there's lots of reasons why people pick different ones, but there's really only a handful of distributions that have achieved critical mass. And we'll need to go through something similar from an evolution standpoint. So to illustrate this a little more, this is an excerpt from the RISC-V.org site where there's just a registry of processor cores that are out there that implement RISC-V. And these are all the open ones. And I took this screenshot or made these tables out of what's on the site probably a couple of months ago. So I guarantee that it's out of date. And the absolute value of the answer here is not important. The fact that there's lots is what is the point I'm trying to make. And there's more coming. So again, happiness, innovation frontier, new barriers removed, that's great. But this is a bit of a problem. So these two in particular, actually, implementations are the subject of what we're going to be talking about today, and in fact, what's in the Vega board that you have. One of the cores is in there. And these are cores that came out of an organization called ETH Zurich. We'll talk about that more in a minute. And these are the ones that we want to prop up and gain more and more industry support around these system Verilog-based implementations. Okay, so the Open Hardware Group and the Core 5 family. So this is a global nonprofit organization. We have international support. It's registered federally here in Canada, based in Ottawa. We're going to take over the world with processor cores, one little city at a time. And here's all the companies that are supporting getting this organization off the ground. We just incorporated in the spring. We're in the process of defining the governance rules, bylaws, and membership agreements and so on, and how to control the participation, or how to encourage the participation. And we have a lot of really good support, so it's very cool. So I mentioned ETH Zurich a second ago. How many in the room, other than the people who know this already, have ever heard of ETH Zurich? Oh, that's pretty good. So that's Albert Einstein's university. And here in North America, not that he owns it, but that's where we went to school. Here in North America, we certainly know Berkeley and MIT and Waterloo and U of T and Ottawa U, bigger engineering schools, Princeton and so on. Most folks haven't heard about ETH Zurich, but I can tell you they're a top 5 ranked worldwide computer science architecture school. These two cores in particular, the 32-bit RISC-V core, they got funny with the 5, and that's an S. In the RISC-V name, and the Ariane, the 64-bit core. These are system Verilog implementations that have gained a fair amount of industry traction. So guys like NXP and Silicon Labs and Thales and other big companies, and Alibaba, saw all the logos on the previous page, went and started playing with these cores on their own and went, hey, these are pretty good. But go back to that analogy of you're going to put your badge on your boss's desk and say, I'm going to bet my career on a core that I downloaded from a university repo. So part of the effort is working with these guys to curate those cores, update the functionality, support them like any piece of commercial IP. So in the Vega board that you've got, the NXP guys did something pretty cool and took an existing product, which I'll show a block diagram in a second, and dropped a couple of RISC-V cores into it, and that's the chip that's on the Vega board. It's not available for sale. You can't buy the chip. It's really for this kind of enablement and research to foster a community that can share and learn more that everyone then can take advantage of. We're really happy with NXP's support to get this off the ground. And so both the RISC-V core and the Ariane core are the first two cores in what we're calling the Core 5 family of open source processors. And this is the RISC-V core. So there's two variants in there, RISC-V proper and then a smaller one called Zero RISC-V, as well as an M4 and an M0 from ARM. And this was literally bringing up an existing product, adding RISC-V to it, and then being able to just take that entire application environment over and put it in the hands of developers. So you'll get that experience later today. All right, so how are we governed? We have it's an open organization. We have a board of directors. In fact, our chairman is sitting over there. I'm going to embarrass him for a moment. Rob, wave to the crowd. There we go. That's Rob Oshana from NXP. He's the chairman of this nonprofit organization, the Open Hardware Group. And we have executives from Blue Spec, Silicon Labs, and Alibaba on the board. And we'll have more. It's a very interesting time right now, launching a startup. I mean, yeah, it's a nonprofit startup, but we're launching a startup, which is lots of fun. All the IP that we work on will be free and open and permissively licensed for everyone to use. Cores, tool chain, to support the cores, and for everyone to use. We'll have trademarks associated with the cores, and if you're using the cores in either research or a non-revenue generating application, you get ready access to the trademarks. If you want to use the artifacts in a commercial product, we simply ask that you become a member of the organization, and that's how you get the license to the trademarks. If you don't want to use the trademarks at all, you don't have to. You can take the IP, call it whatever you want, fork it, do whatever you want with it, and away you go. So in particular, the role of the organization is to maintain online repositories of all of the documentation and the IP available for everyone, and we'll sustain that and evolve it depending on the requirements from the community and the membership. So there'll be a roadmap associated with each of these cores and obviously register and manage the licenses associated with the trademarks. So the way that an organization like this works is the board of directors is just like the board of directors of any other company. They oversee the operation of the board of the company and make sure that we're executing against our purpose. And the way that happens is we have two main working groups in the organization, a technical working group that's going to manage all of the implementation, and a marketing working group that will do events and promotion. And the working group participants are members of the organization, but anybody at large can participate in any of the online work, and you'll see that. I can talk about that more probably during the break. So here's just a view of what the working groups and subgroups look like. So there's a cores task group that will evolve the roadmap for the cores. There's a verification task group that will turn this IP into industry quality IP, and then a platform task group that will do things like the Vega board and bring up environments for evaluation. And then your typical kind of marketing activities too will happen within the organization. Right, so where are we? Like I said earlier, it's a legally registered nonprofit here in Ottawa with a global footprint of developers in North America, Europe, and Asia. It's kind of cool that our partner school's in Zurich, which is nice. We actually launched the organization at a workshop in Zurich in June that was hosted on campus at the university, which is great. Make sure you follow us on the various social media channels. And we're open for business. If your company is really passionate about this, or as an individual you're really passionate about this, take the initiative to join us and help shape how we're going to change this landscape in our ecosystem. So that's the end of my talk. I hope I've conveyed that RISC-V overall has massive support in the industry. The Open Hardware Group is a relatively new organization, and we've got over 20 partners and sponsors now, and very, very stable cores that we're inheriting from the university. And the other part that I didn't really focus on is the intent is that these cores are going to be supported through commercial tool flows. Big chip companies build their chips using, either Cadence, Synopsys, what have you, tool flows, and that's how we're going to support these tools as well. And like I said, it's an international organization. So it's enough of me. That's the end of my talk, and we'll come back to the agenda here so that we can move on to the next speaker.